Okay, so let's give this a shot here. We're going to talk about something that we talked about yesterday, binomial distributions and binomial experiments. Just kind of a review of some things here. Symbols. I'm going to look at some symbols here. The number of times the trial is repeated is n, and that's always a fixed number. You'll know that number. Small p is the probability of a success. Little q is the probability of failure, and q is equal to 1 minus p. So let's say that we are talking about a 4-question test. Okay, and let's say that you're guessing, or it's not a 4-question, it's a 4-answer test. 4-answer test. So you have prop A, B, C, or D. Okay, what's the probability of a success? Well, if you're guessing and there's 1 out of 4 that's right, your probability of success is 0.25. Probability of failure is going to be its complement, 1 minus 0.25. Okay, so that's what P and Q are again. And X is the number of successes that we're trying to find the probability of. So we might be trying to find the probability of on an experiment with 3 trials. Maybe we're trying to find what's the chances that X equals 2, that there's exactly 2 successes. Sometimes we'll write it like this. Sometimes we won't write X equals. We just assume that we're talking about the number of successes as 2. So you might write it like that. Okay? Okay, so let's determine if things are a binomial experiment or not. I'm going to give you the acronym BINS. It needs to meet all 4 requirements. Number 1, it must be binomial. That means there must be 2 outcomes for each trial. Each trial must be independent of one another. For example, you can't take a set of cards and not replace the item, because if you do that, then each probability changes, and the new pick has a probability that's dependent on the old pick, so the probabilities change, so those would not be independent. Okay, they need to be independent of one another. Each probability must. N stands for number. Okay, the number of trials is fixed in the experiment. You aren't going to say, hey, if there's going to be 5 questions or 4 questions, you're going to have a fixed number of trials. And then S, the probability of success is the same for every trial. Okay, so let's take a look and see if it meets these requirements here. If it is, let's try to find the value of N, P, and Q, and list the possible values of what X could be that we might want to find. So a certain surgical procedure has an 85% chance of success. A doctor performs the procedure on 8 patients. The random variable represents the number of successful surgeries. So binomial. Well, we have to kind of understand what a trial is. And they're kind of talking about 8 patients here. So the first patient might have success or not. They might do well on that, or they might not. So there are 2 outcomes. You can have successful surgery or an unsuccessful surgery. Okay, are they independent? You know, I think that we're saying in general the surgical procedure has an 85% chance of success. So I think we're assuming here that each surgery is independent of the other. One isn't going to decrease its percent of probability of success compared to the prior one. So I think we're going to assume that they're independent. Is there a certain number of trials? Well, yeah, I think we kind of say that N equals 8. That's the number of trials. And again, each one is either going to be successful or not. Is the probability of success the same? I think that we have said that it is, and it's going to be 0.85. So then Q would be its complement, 0.15. So we have N, we have P, we have Q, and what are the possible values of X? Well, you could have 0 successes, not likely, all the way up to 8 out of 8 of the surgeries being successful. So it is binomial, and those will be our values. Okay, next one. Jar contains 5 red marbles, 9 blue, and 6 green. You randomly select 3 marbles. So we're picking one, and we're picking another, and picking another. So I think there's 3 trials. I think we can assume that there's trials, with each trial being a pick of the marbles. Now, without replacement, so we're not replacing each item. So what that would do there is that would create a dependent situation, because the probability of the second pick would change because there would be 1 less marble than there would have been on the first pick. So we're going to have to say that this is not a binomial experiment. So then let's not worry about finding N or P or Q in that situation. Okay, so a formula that you learned yesterday. Again, we might say, what's the probability that X is equal to a specific number in there? Okay, but here's your formula. Let's see if we can practice this formula here. So, microfracture knee surgery has 75% chance of success on patients with degenerative knees. The surgery is performed on 3 patients. Find the probability of the surgery being successful on exactly 2 patients. So I would always write down what N is, what P is, what Q is. I would do that. And again, I've decided that it is a binomial problem. Maybe review that. Is each trial independent, or is each trial have 2 outcomes? Yeah, either successful or not. Each surgery is a trial. Okay, so we're either going to have success or not. Are they independent of one another? Again, like the previous example, I think we're kind of assuming that they are independent. Are the number of trials fixed? Yeah, I think we know that the number of trials is 3. We're interested in the chances of 2 successes, 2 patients having success, but there are 3 trials. The probability of success is the same on all of those. I think we can assume that. So P is 0.75, Q is 0.25, and we want to know the chances of the number of successes being 2, or probability of the random variable being 2. So using our formula, let's say that we have our number of trials is 3, so 3 choose 2 times the probability of success to the X, and X is 2 in this case. We're having 2 successes, times the probability of failure. We're having 1 failure. So let's work that out. So get your graphing calculators out. I have a graphing calculator right here that I'm going to show you the steps for typing that in. Now, if you know this number, maybe you can calculate it, maybe you can put it in. I think I know that that's 3, but let's see if we can plug that in. So I'm going to go second quit. It takes me to the home screen. I'm going to clear my home screen. Just works just like the screen, just works just like a regular graphing calculator. Okay, so I'm going to go 3, math, PRB. I'm going to arrow over. I'm going to go down to NCR, and we're going to hit enter there, and we're going to type in 2. And let's take that times our probability of 0.75, the probability of success, to the second. Got to get that cursor out of the exponent and take it times 0.25 to the first. So you can put a 1 up there if you want to. Let's go 1. And let's hit enter, and that's going to be the probability of exactly 2 successes on the 3 trials. I lost that, so 0.422. Okay. Let's move on to the next page, see what's going on the next page here. Looks like we have another problem here. Another micro fracture knee surgery. Still the same probability of success, 75%. Find the probability that you'll have we already did that one. Already did that problem. Don't need to do it again. Oh, jumped ahead. Sorry about that. Okay, so let's take a look at this one here. Now there is a number here that is going to come into play, and I want to make sure that we have that. That number is 56% right here. So we'll talk about what that is as we go through the problem. Okay, so it says in a survey, and these are the results of the survey right here. U.S. adults were asked to give reasons why they liked texting on the cellular phones. 7 adults who participated in the survey are randomly selected and asked whether they like texting because it's quicker than calling. And that's the percent that said that they liked the fact that it was quicker than calling. So that it's kind of hard to read there. So that's the only piece of information we're going to use from that. We're not going to use the other information. So create a binomial probability distribution for the number of adults who respond yes. So we're going to try to fill in this table. So let's again kind of think about if it's a binomial, is there 2 options? Well, maybe the first thing we need to do is understand that each trial is the asking of a person if they like texting because it's quicker. So success I think I got that right now. Success is that they are going to say yes. They do think that it's quicker. So there is success. They would maybe say that it's quicker at 56% of the time. So little p is 0.56. Little q would be its complement, 0.44. There are going to be 7 adults who are asked. So each adult being asked is a trial. Again, think about the crazy Venn diagram that you could have, and we're going to write the results, really, of the tree diagram. Excuse me, the tree diagram that we talked about the other day. And we're going to use our calculator for this, so make sure you have your calculator out and ready to go. Okay. So we've got 0 through 7 for x, and we're going to calculate the probability again using our calculator. So if you remember, binom PDF n comma p is going to give you a string of values. So we're going to get our calculator out and let's see if we can use that calculator. Okay, so we're going to be in the distribution menu, and we're going to go down until we see binomial. Binomial PDF, and we're going to hit enter there. And the number of trials, we've already done this, the number of trials is 7, and the probability of success is 0.67, and we want to calculate, no, probability of success is not 0.67. Number of trials is 7, probability of success is 0.56. And we're going to enter in nothing. I'm going to delete that. I'm going to have nothing there. And we're going to enter that in and let's see what happens. Let you make sure you have that typed in. Okay, so the first number is the probability of 0 successes. Okay, so what I'm gonna do is I'm gonna write. You won't be able to see this, but I'm gonna write these on the whiteboard so that I can remember them. We go to 3 decimal places. You write them on your table as we go. So this would be the probability of 0 successes, 0.003. I'm having trouble seeing this. So I'm gonna do something that will help you view the problem better too. So let's do this again. I'm gonna hit second enter. I have no trouble here. Second enter. It's the previous command, and I'm gonna hit the stored button. And I'm going to store this data into list 1. Now, if you miss that, that's not that big a deal. It's just going to allow us to see this information a little bit better. So I'm going to go to the stat menu, and I'm going to look at my data. So there's our probabilities of 0 successes. The first one is 0 successes. This was probability of 1 success. 2, 3, 4, 5, 6, and 7 successes. It's the maximum number that you could have. Now, notice that this is 8. That's the 8th term in the column, but remember that you started at 0. So I'm going to write these down on the whiteboard, and I'm going to have you write them down as well. So 0.003, 0.028, 0.109, right here, 0.230, 0.293, 0.224, 0.095. Arrow down so I can see the rest of it. And that is it. Oh, no, we got 0.017. Okay, now I'm going to record those in my table. So 0.003, 0.028, 0.109, 0.230, 0.293. I think that was. I can't read it. It looks like a 9 or a 4. 0.224 and 0.095. Last entry 0.017. So let's think about that. The chances of having 0 people say they like it because it's quicker, very low. Probability of all 7 of them is actually low as well. So you're going to have in general between 3 or 4 or 5 people maybe say that they like it because it's quicker. It's going to be tough for all of them to say that they like it, and it's going to be tough for all of them to say that they don't like it. Now, one other thing that you will be doing today is you'll be making a diagram here. You'll be making a histogram of it. On this horizontal axis, you're going to put your x values. And the x values is the number of successes. And on this y-axis, you're going to put the probability, and the probability is going to range up to about 30%. So I'm going to scale it by 10%. So I'll let you make that diagram if you'd like to. And then we're going to just put bars up as high as the probability for each event. That's maybe a little bit high. Probably shouldn't be much of anything there at all. 2%. One trial has a probability of 2%, 1 success. 2 successes has a probability of happening 10% of the time, but you'd have 2 successes out of the 7 trials. 23%. 4 successes, about 30%. 5 about 22%. 6, about 10%, a little less than 10%. And then 7, barely 1%. So center the bars around the number of successes that we're representing their probability with. Now, one thing that you will note is that if the probability of success in an experiment is 0.5, your histogram will be symmetrical. If the probability of success is more than 0.5, we would expect to have more successes than not. You know, if we had a chance of making free throws 99%, you're going to expect on, say, a trial number of 4 to have higher bars on the 4 number of successes and the 3 than you would than the 0 and the 1. So that would mean that you would have a skewed left. The extreme values would be on the left. You would not have 0 successes very many times. If you have a probability that's high, you're going to have bars that are going to be high on the right side, not on the left side. And if the probability of success in the experiment is less than 0.5, then you have a skewed right. Okay, so we've already done this problem here. We don't need to do that one again. Let's try this problem. You aren't going to have to graph the whole thing. You are going to have to find the probability of at least 2 of them responding yes. So again, let's read the problem. So a survey indicates that 41% of the women in the U.S. consider reading their favorite leisure time. You randomly select 4 U.S. women. So I think we're probably looking at our number of trials being 4 because each trial is going to be asking a woman that question. And they're going to respond, yes it is, or no it's not. So it's a binomial situation. The probability of them responding yes, in general, is 41% of all women. So each woman has a 41% chance of saying yes, that is her favorite activity. So find the probability that at least 2, that would mean x is greater than or equal to 2, which would mean that you could have 2 successes out of 4, or the number of successes is 3 out of 4, or 4 out of 4. So again, let's use our calculator. And let's clear this. Got to go to the home screen. Second quit to the home screen. There, clear the home screen. Okay, so the distribution that we're looking for is the binomials under distribution. So second bars, we are going to go down until you see binomial. It's going to be option 10 or option A. Option A. So let's enter that. Number of trials in this case. Asking 4 people, so that should be 4. Probability of success, well, you have a 41% chance that somebody's going to say that they like to read, that their favorite activity. Now we're going to leave x empty. Remember, binomial PDF n comma p will give you the entire string. If you added a k here, it would give you only that one value. So we want the whole string, so we're not going to enter anything in here. So let's go down to paste, and let's hit enter. Again, I probably should have, there we go, we can see it that way. So if you use your arrow, you could see the probability of 0 successes right there at 0.121, which we're not interested in. Here's the probability of 1 success, 0.337. Not interested in that. This is the probability of 2 successes, 0.351. Interested in the probability of 3 successes. So 0.163. And we're interested in the probability of all 4 being successful, which is the last number, 0.028. Then you add those all up. If you add all those up, you should have your total. And you end up getting 0.542. So the probability of having 2 of the 4, or 3 of the 4, or 4 of the 4 say that it is their favorite activity is 0.542. Just maybe to review one more thing here. Again, if you want to look at the data in a list, I'm going to recall my last entry, hitting second enter, and I'm going to store that data into a list. List 1. So now if I go back into my stat menu and I edit my data or look at my data, I should be able to see those numbers without having to do as much work. So that's a probability of 0 successes, 1 success, 2, 3, and 4. Okay? And you could use that to make your histogram if you needed to. Okay, we're getting there. Now, we're going to talk about one more thing here. We're going to talk about the mean, the variance, which we're not going to use that much. You usually use standard deviation, which again is just the square root of the variance. Now, these are the mean standard deviation of a binomial probability distribution. Okay, if you don't have a binomial, then you have to go back to your previous formula, which we learned is summation of x times p of x. So this is just a regular, ordinary probability distribution. The standard deviation was the square root of summation of x minus mu squared times p of x. So those you could use. You're not going to use those now. You have a shortcut here to find the mean and standard deviation. Okay, so let's go ahead and do that. So it says in Pittsburgh, Pennsylvania, about 56% of the days in a year are cloudy. Find the mean, variance, and standard deviation for the number of cloudy days during the month of June. So again, let's think about this. So each day in random has a 56% chance of being cloudy. So let's say that we wanted to make a probability distribution. You don't have to do what I'm doing right now, but you'd have anywhere from 0 through June has 30 days, I believe, in it. So June has 30 days, even if it doesn't. We're going to say that it does. And we want to maybe make a distribution, and in this case, we want to find the mean, the variance, and the standard deviation. So the number of trials is 30. So you either have of the 30 days, there might be 0 that are cloudy, or maybe all 30 are cloudy. Not very likely. You're more likely to have probabilities in the middle of number of days that are cloudy. But what would be the mean of this distribution? The mean of this distribution would be n. So the number of trials in the month of June, again, either the first day is or not, second day is or not, third day is or not. You're going to have a really weird looking tree diagram, but there'd be 30 sets of branches. That's each trial is that, and probability of success is 0.56. So each day has a 56% chance of being cloudy. And so if you multiply that together, you get 16.8. So on average, you'd have about 16.8 days of cloudiness, and if you stick these numbers into your standard deviation formula, you have 30n times 0.56 times 0.44, and if you work that out, that ends up being about 2.7. So the standard deviation of that is 2.7. Remember, that's a measure of spread. So let's find the mean, variance, and standard deviation, and then let's talk about how to describe any unusual events. So this is the last thing we're going to talk about here. Okay, so on average, there are 16.8 cloudy days during the month of June. The standard deviation is about 2.7 days. So give or take 2.7 days, that's going to include a majority of the data. Values that are more than 2 standard deviations from the mean are considered unusual. So let's take the mean and let's subtract 2 standard deviations, and you would get 11.4. So the mean minus 2 standard deviations. Kind of like thinking about the normal distribution. Remember we said 95% of the data is within 2 standard deviations of the mean, mu plus 2 sigma, mu minus 2 sigma. So it would be a rare event to be either above or below that value. Okay, that's what we decided that we would consider unusual, is if it had a probability of 5%. So this totals up to be 5%, so your chances of landing there would create an unusual situation. 16.8 minus 2 times 2.7 would be unusual if it was below that or above 23. So we rounded it down and we rounded it up, because if we rounded this up, that would kind of shrink that middle percentage. Again, don't worry about this too much. But that would be your description of the distribution. So, good luck.